Okay, welcome to our first video lecture on section 3.5. That's about zero and repeated eigenvalues. So we're still looking at linear systems of the form y prime equals some matrix, which we'll call A times y. We're still going to be finding our solutions by finding eigenvalues and eigenvectors, but we're actually back to the real numbers now, because we're going to be looking at what if 0 happens to be one of our eigenvalues. Up until now, we've had positive numbers, we've had negative numbers, and we've had complex numbers, but we haven't had 0. And then what if I have a real root, but it's a repeated root to the characteristic equation? Okay. So in this particular video, I'm going to give it away. We're going to be taking a look at what happens if 0 is an eigenvalue. So I'm going to start by finding the eigenvalues for A. If you would like to pause the video and try to find the eigenvalues and then double check your answer, you can always, you can come back. You can fast forward to where I say what the eigenvalues are. If you agree, you can just keep going. If you don't agree, you can go back and watch and see where you went wrong. Okay, so I'd encourage you to do that. Okay, welcome back. So A minus lambda I would be the matrix 2 minus lambda 1, 4, 2 minus lambda. So the determinant of A minus lambda I is 2 minus lambda squared minus 4, which is lambda squared minus 4 lambda plus 4 minus 4, which is lambda squared minus 4 lambda. Now that's just the determinant. My characteristic equation is when I set that equal to 0. Lambda squared minus 4 lambda equals 0. Well, that would mean lambda times lambda minus 4 is equal to 0. So lambda is equal to 0, or lambda is equal to 4. So I have two eigenvalues, but we can see one of them is 0 and one of them is 4. Okay, so I'm just going to write down here lambda 1 is 0, lambda 1 is 4. At this point, we need to find an eigenvector for each of those eigenvalues. Now, we do know that we have two distinct real eigenvalues, which is fantastic. We can find the general solution, no problem, because we can find a solution associated with each eigenvalue and build it out of there. So what's going to be new is, how does this affect what the phase portrait looks like? But let's go ahead and find our eigenvectors. Again, I would encourage you to pause the video, try to find them on your own, and then turn it back on and see how you did. I'm going to work it out here. Welcome back. So if I'm looking at lambda 1 equaling 0, okay, then I'm basically looking for A minus 0i times some non-zero vector v1, v2 has to equal 0, 0. Okay. Well, that's just 2, 1, 4, 2 times v1, v2 equals 0, 0. The corresponding system is 2v1 plus v2 equals 0, 4v1 plus 2v2 equals 0. And I can see that's a dependent system because this equation is just 2 times that equation. So if 2v1 plus v2 equals 0, 2v1 is negative v2. So I'm just going to choose as the vector v1, I'm going to choose to let v1 be 1, then v2 would have to be the opposite of 2. That way 2 times 1 is equal to 2, which is the opposite of my negative 2. Awesome. So we've got a corresponding eigenvector there. v1 is going to be 1, negative 2. Now let's find one for lambda equals 4. And I'm sorry, I wrote lambda 1 equals 4. That should be lambda 2 equals 4. So now we're looking at A minus 4 lambda times some vector. I'm just going to recycle the variables v1, v2 equals 0, 0. So A minus 4 lambda is going to become negative 2, 1, 4, negative 2 times v1, v2 equals 0, 0. So the corresponding system of equations is negative 2v1 plus v2 equals 0. 4v1 minus 2v2 equals 0. Again, clearly a dependent system because this equation is just negative 2 times this one. Solving this one, I'm going to get v2 has to equal 2v1. So I will choose as my vector v2, I'm going to choose v1 to be 1, and then v2 will be 2. So the eigenvector for my second eigenvalue is 1, 2. Excellent. So let's go ahead and build our general solution, and then we can come back and talk about the phase portrait. So my general solution is going to be y is equal to a copies of e to the 0t times v1, which is 1, negative 2, plus b copies of e to the 4t times 1, 2, okay, where a and b, of course, are real numbers. Okay. So that's just a copies of 1, negative 2, because e to the 0 is always going to be 1, plus b copies of e to the 4t times 1, 2. All right, excellent. So now let's take a look at our phase portrait. So in the xy plane, I want to draw my equilibrium solutions. Well, I'm used to drawing just one equilibrium solution. But here, because 0 is an eigenvalue, I actually have infinitely many equilibrium solutions. Anything that's an eigenvector corresponding to 0 corresponds to an equilibrium solution. So here, we're used to drawing a line of straight line solutions, which would be these rays either approaching or leaving the origin. Now, I'm still going to graph this straight line solution coming over 1 and down 2, but there are no arrows on that. Let's make that slope a little bit better. Every point on here is an equilibrium solution, because the point 1, negative 2 right here, that corresponds to this eigenvector. That's something that if I plug it into y, when I multiply by this matrix, I get 0. The derivative is 0. If the derivative is constantly 0, I'm at an equilibrium solution. So every single point on this line is an equilibrium solution. Okay. And so I indicate that by not putting arrows on it. Okay. Now, I can draw the straight line solutions associated with my other eigenvalue, which was 4. That's going to be the line determined by the vector 1, 2. So over 1 up 2. We'll have 2 half lines. Since my eigenvalue was 4, which is positive, we're simply moving away from the origin. So I've got the origin here. These solutions move away. These solutions move away from the origin in a straight line. Okay. Now, what do our other solutions look like? It's kind of interesting. I'm used to, in each region, sort of starting out behaving like this and ending up behaving like this, or vice versa, okay? But that usually involves some curving. But let's suppose I do start out behaving like this, because it does seem, since I've got a positive eigenvalue here, my solution should be moving away ultimately from equilibrium. If I start behaving like an equilibrium solution and then end up behaving like one of those, I'm just going to get a straight line solution that's parallel to that one. That mirrors the start behaving like one of these, end behaving like one of those pattern that we've seen before. Let's see if the algebra plays out. Okay. This right here would correspond to basically x is b e to the 4t, y is 2b e to the 4t, which is y equals 2x. That looks like a straight line solution, because that's in fact what we're doing. What I'm adding to it is just a constant. When I add a constant to it, that doesn't make it curve. That just picks that straight solution up and puts it in another location. So I'm just translating my straight line solutions so that instead of the equilibrium solution that they're moving away from necessarily being the origin, all of my other non-equilibrium solutions are straight line solutions going away from one of the equilibrium points that's on this line of equilibrium solutions. Very cool. I like.